So Amin gave a very nice talk on out of time order correlators already, so I'll probably go through the first few slides very quickly. So yeah, so this is a outline of my talk. Right. So yeah, so as Amin mentioned, out of time order correlators are not so well studied objects in for quantum mechanical systems, but they may encode important information about this about these systems. As I mentioned, they come up in two OTO correlators come up in discussions of chaos. They come up as a measure of chaos, but higher OTO correlators haven't been studied that much as yet. But it is interesting to explore such OTO correlators, such higher OTO correlators, and see whether they tell us anything new about the physics of the system. So, yeah. So one possible area where one can do such a study is a system which is in contact with a thermal bath. And here we assume that the bath is made up of a bunch of harmonic oscillators, and the system bath in is in some earth power in the bath degrees of freedom, where R is greater than or equal to 1. And yeah, this is the action of the system plus bath, the total system. And here Jt is a function of, so Q denotes the degree of freedom of the system in which we are interested, and X are the degrees of freedom of the simple harmonic oscillators, and this Jt that gets coupled to these x to the power r coordinates. I'm denoting this, I'm giving this arrow because there can be more than one. There can be, since we have a bunch of harmonic oscillators, collectively I'm denoting all the coordinates by this vector, and this j or q are also the coordinates of the system. So Jt is a function of Qt, and the coupling constant is lambda. Now we can integrate out the degrees of freedom of the bath to construct an effective theory for the system only, and then we can study the behavior of OTO correlators in this with help of this effective theory, and see when such a system is brought in contact with the thermal bath, how this system thermalizes. That is, when it is out of equilibrium, thermal equilibrium, study the behavior of these OTO correlators. And for this one needs an efficient formalism which allows one to calculate such correlators, OTO correlators, as Amin introduced, gave a sketch of the formalism. It's this a generalization of the Schwinger-Keldysh formalism. I'll talk about it later in the talk. Yeah, but yeah, so as I'll explain later, there's a redundancy in this formalism, and for thermal states, when we are dealing with thermal states, there's a way in which these correlation functions in this generalized Schwinger-Keldysh formalism can be expressed as that this redundancy is manifest, and such that these generalized Schwinger-Keldysh correlation functions can be expressed clearly in terms of the truly independent quantities. The truly independent quantities are the ones that Amin mentioned, the n-1 factorial. In a thermal state, you have n-1 factorial independent Weitman correlators. So this column vector representation that I'll be talking about, that actually expresses these contour correlators, the correlators in the generalized Schwinger-Keldysh formalism, in terms of those independent quantities. And then one can, once one has information about, if one is able to calculate these independent Weitman correlators, and if one has these contour correlators in terms of these independent Weitman correlators, one can construct this effective theory. One can integrate out the degrees of freedom of the thermal bath and construct an effective theory for the system. Okay, so this system that I was talking about, this for the R equal to 1 case, where the coupling is linear in the degrees of freedom of the bath, that was considered by Feynman and Vernon in 1963, and so for simplicity, let's take a simple system. Let's take a Brownian particle interacting with this harmonic bath, and this interaction is linear in the degrees of freedom of the simple harmonic oscillator, which I denote by xi. There are n oscillators, and so this is the Lagrangian of the system. Lambda I mean the different harmonic oscillators can couple to the degrees of freedom of the system with different coupling constants. So lambda I are the corresponding coupling constants, and Q is the analog of the quantity J that I had defined here. Q is a function of the small q, which is the degree of freedom of the system in this case.
You don't consider coupling because of simplicity of
Yeah. In this case, yeah. I'm just considering a coupling which is function of x. Now, one can consider a Schwinger-Keldysh generating functional. One can, So the Schwinger-Keldysh formalism is a formalism to deal with possibly mixed states, and also consider not time-ordered correlation functions, but also time-ordered correlation functions and 1-OTO correlation functions. So I'll talk about it. I'll talk about a generalization of that. But one can consider this Schwinger-Keldysh generating functional, which is defined as such. So rho is the density matrix of the system, and then you basically couple to the Ket fields. You couple. You consider a source for the Ket fields, which is Jr, and a source for the Bra fields, which are Jl, and these two are not necessarily equal, and hence these two don't cancel each other. If they were equal, then you by cyclicity of trace you could bring u to the end of this trace, and they would have cancelled, but and then you would have got just trace rho, which is 1. But if the sources are not the same, then you have something that is not trivially 1, and you can basically you can express this as a path integral on a contour with one time fold, where the original degrees of freedom are doubled. As I mentioned, I'll discuss a generalization of this, so I'll not go into detail right now. So, but basically what one can do is that one can differentiate with respect to these sources and get correlation functions in this Schwinger-Keldysh formalism. So now integrating out the degrees of freedom of the bath in this path integral, we can get the effective dynamics of the particle, which is encoded in a quantity called influence functional, which is basically what you get by integrating out just the additional term that gets multiplied to the original function that was dependent on the degrees of freedom of q in this path integral, by integrating out the degrees of freedom of the bath. So this influence functional is one can consider the logarithm of the influence functional, since we are dealing with a free theory, a theory which is quadratic in this case. So basically, the harmonic oscillators are quadratic, and so basically when you integrate out the degrees of freedom of the harmonic oscillator, this acts as a source. Basically, this q acts as a source, and you can do an expansion in this source or in this coupling lambda I, but the quantities that are going to appear are basically Schwinger-Keldysh contour correlators. The coefficients that you will get corresponding to this expansion are the Schwinger-Keldysh contour correlators of X, and these contour correlators are calculated for this quadratic theory, and hence you can basically apply Wick's theorem, and you can get the entire expansion by exponentiating the 2-point functions. And in this case, once you the quantity that you exponentiate is called the influence phase, and in this influence phase, which is a 2-point function, which is obtained from 2-point functions in the Schwinger-Keldysh formalism, and these 2-point functions basically there are 2 types of 2-point functions which come up. One is this commutator and another is this anti-commutator. And these commutators, actually what Feynman and Vernon showed was that these commutators contribute to the dissipative term in the Schwinger-Dyson equations of the particle. Whereas the anti-commutators, they contribute to the noise terms in the same equations. And as Amin mentioned, the KMS relations connect these two quantities, and hence we have a fluctuation dissipation relation in this context. But for the linear coupling, as I mentioned, for linear coupling, you can only, this influence phase contains only 2-point functions. And for 2-point functions, you can't get anything more than 1 OTO correlators. This is also what Amin mentioned. In order to get 2 OTO correlators, you have to go to at least 4-point functions. So in this case, you can't get 2 OTO correlators. So only 1 OTO correlators come up, and yeah. So the equation of motion of the particle is, all information about it is obtained from 1 OTO correlators. Now, what one can ask is that, suppose if we have nonlinear interactions, interactions which are nonlinear in the degrees of freedom of the bath, then what are the imprints of the higher OTO correlators of the bath on the equations satisfied by the correlators of the system, and whether there are some analogous dissipative and noise terms, and if so, can one find a fluctuation dissipation relations, can one find fluctuation dissipation relations for such quantities?
What would happen if you had a coupling with xi dot? Would be similar.
Yeah, then you probably, yeah, I don't have an answer offhand, but yeah, to get fluctuation dissipation, yeah, maybe, yeah. Right. So to analyze these questions, one needs to actually calculate these influence functionals for such interactions in the generalized Schwinger-Keldysh formalism. So now I'm going to explain what this formalism is. Consider a system which is described by a unitary theory and which is defined on a set of fields, which I'm calling collectively phi. Let O1, O2, On be n functions of phi, the usual operators in field theory, and in this formalism, one can calculate k-OTO correlators where k is any positive integer, and what one does in this formalism is that one considers 2k copies of this field, of all these fields, which I am collectively calling phi, and then one does path integral over a certain contour, and this contour is indicated in the next page. So the contour is a k-fold contour, that is, it has k future turning points. Amin was talking about future turning points in his talk. So in this case, you have k future turning points where you can put those k future turning point operators that Amin was talking about. So you need for k-OTO correlators, you need such k-fold contours, and this path integral is basically on each of these contours you put on each of these legs in the contour you define a copy of the field and you identify the fields on two successive legs when they are joined by a turning point, and you put an insertion row at some time t0 where basically you put an insertion row and you integrate. You can add sources corresponding to each of these fields, or more generally you can add sources corresponding to operators which are functions of fields, and by differentiating with respect to those sources you will get the corresponding correlation functions. Right. So these are you can put insertions. So these correlation functions are, I mean, since the fields get multiplied by 2k, you have 2k copies of fields. The operators O2 ON, they also get you have 2k copies of these operators as well, because they are functions of these fields, and so basically these, so in this formalism you can calculate basically contour ordered correlation functions, where contour ordering in this case means that here you have an arrow along the contour. So basically as you move along the arrow, if you encounter insertions, you put the first insertion that you encounter, you put it on the rightmost side, at the rightmost point. The first and eventually you go towards the left, right? And the way to connect these contour correlators with the correlation functions in your original theory is that the contour ordered correlators are equal to the corresponding Feynman correlators by just keeping the order of the insertions the same, but drop these indices GR or JL, whatever you had on the O's. You just drop these alpha 1, alpha 2, alpha n are can take values from over these 2k legs, and you just drop those when you calculate the Feynman correlator. So that's the formalism, and here I have showed 3 examples of time ordered, anti-time ordered, and 1 OTO correlators. So if you follow the algorithm that I mentioned, you get these correlators for k equal to 1, and you can see that you can't basically go beyond 1 OTO, because you can just put one operator at this near the future turning point. There's just one operator which is adjacent to the new future turning point. Right. So there are some rules in this which are satisfied by these contour correlators, and that's that when one so consider this contour, and if you let's say you have some insertion at T1 on a right moving leg, and you move it from T1 to T2, then the corresponding Feynman correlator that you calculate, the insertion in that Feynman correlator gets modified by a time evolution operator UT1 T2. So you have OT1, you had initially OT1, that goes to UT1 T2 dagger, OT1 UT1 T2, and that is basically equal to OT2. And now if you move from T2 to T1 along the left going leg, then the rule is just opposite. I mean, you have the operator evolves by UT1 T2 dagger, and hence you basically go back to OT1, and these two are equivalent because, I mean, only if your theory is unitary, and that is for closed systems. For closed systems, your theory is automatically unitary, but if you are working with open quantum systems, generically they are not unitary, and hence these slide rules are applicable for them. Right. So I'll just not go through them, because Amin, I think, has said about these things. So yeah, the K-mesh relations basically relate the Whiteman correlators which are obtained by cyclic permutation, and hence there are n-1 factorial independent thermal I'm talking about thermal Whiteman correlators. So there are n-1 factorial independent thermal Whiteman correlators.
Just to answer that last.
Yeah.
If I look at the whole system,
Yeah, that's a closed system. Yeah.
Then you can slide.
Yeah, then you can slide.
And now in integrating our bar, have you done some approximation?
Sorry?
You can slide the exact result.
Yeah.
And unless you introduce some approximation, you should be able to slide even
Yeah. In that case, yeah. If you consider, let's say, if you integrate out some, if your system is obtained by integrating out some modes from some closed system, then yeah, then you can still perform sliding.
So when can you not? I thought always you get this thing by integrating out some.
Right. So yeah. Let's see. Generically, if you have, let's say, some explicit disorder in your system, then you won't be able to do this. Let's say your correlation functions are calculated by some. You are not actually integrating out some degrees of freedom, but you are introducing some model.
Approximation.
Yeah.
Sorry, can I ask one more general? It's a very basic question, but in general, when you have Lindblad evolution, can you always unitarize it? By going to a larger system and getting a unitary evolution in that system?
I don't know actually. Yeah, I don't think that.
Probably. If not, no. The answer to the question asked.
Okay, if it is finite dimension Hilbert space, quantum mechanics system, yes. Quantum physics,
All physics is finite dimensional. Okay.
Yeah. So I just So the point. What happened? Okay. Right. So basically the point is that in this generalized Schwinger-Keldysh formalism, you can put your insertion, each of these insertions. So let's say you are considering an n-point function. You can put each of these insertions on any of one of the 2k legs. So you can have 2k to the power n contoured correlators. But the point is that, since there are only n-1 factorial independent correlators in your theory, there must be some relations between them. And this column vector representation is just a representation of these correlation functions, which makes this redundancy manifest. And so basically what we do is that we consider all these correlators as an n-dimensional array, where each of these dimension, you put 2k elements on each of these directions, which dimensions, and these 2k elements correspond to which leg you are considering your insertion to be in. Let's say some jth insertion, which leg you are considering, and that there are 2k possibilities, so you will have 2k elements, and so you are considering an n-dimensional array. And so the point is to choose a basis for this 2k dimensional column vector along each axis, and then take tensor products of these basis vectors to construct a basis for this n-dimensional array. And if you choose your the basis for the 2k dimensional space cleverly, then many of the components for this of this n-dimensional array in this tensor product basis will automatically be 0. And so one such suitable choice of basis for column vectors is this, where this j is run from 1 to k, and this f quantity is just the Bose-Einstein distribution. And one thing to note is that this is a function of omega. So we choose for each omega, we choose a particular basis, and notice that this doesn't work when omega, this basis basically the elements in this basis diverges when omega is equal to 0, as you can see from the definition of F. And the dual basis of this is given below. And these labels P and F basically indicate, so in EP and EF we just have two elements which are non-zero, and the P and F indicate whether the two non-zero components are on legs which are connected by past turning points or future turning point. So yeah, you can now take tensor product of these basis vectors E bar to construct a basis for the n-dimensional array. And you can look at the components, and the components are basically, so the point of choosing these basis vectors is that many of the components are 0, and the reason for that they vanish is that is the sliding rules that I mentioned earlier. So basically the two non-zero components for EP and EF, so in order to get the component along some E bar, which is a tensor product of as shown in this slide, one has to contract with the corresponding tensor product of the E's, and if one such, I mean often what happens is that the two components in one of the E's in the tensor product basically cancel each other's contribution. When you contract with these basis vectors, they cancel each other's contribution. Right. So this is the column vector representation for 2-point, 3-point functions. As you can see, for 2-point functions, there's just one can express it in terms of just the commutator, and for 3-point functions, you have just two elements, which are these nested commutators. But not for 4-point functions. For 4-point functions, we have nested commutators as coefficients, but also such products of commutators. So the point is that, yeah, I mean nested commutators, yeah. So and one thing that I would like to mention is that these expansions work only when omega is not equal to 0, because the basis which we chose was for omega not equal to 0, and this will work nicely if the operators that we are considering do not have any delta omega I type of term. Then we can then basically the Weitman correlators won't also have anything like delta omega I, and in that case we can work with these expansions. But if the operators that we are considering also have something like delta omega I, which is true for instance for the harmonic oscillator, but say x doesn't have anything like delta omega in it, but x square, if you consider x square that have such terms, so one has to be careful. Right. So just let me talk about this this case that I was saying. It says, so let's say let me go back to this case of a system which is brought in contact with a harmonic bath, but now consider just give me 2 minutes. Now consider that the coupling with the harmonic bath is x square, and then basically one can write down a path integral in this generalized Schwinger-Keldysh formalism, and one can integrate out the degrees of freedom of the harmonic bath. And what one can see is that from this expression one can see that the harmonic, so you can see that the expression that you have, if you integrate out the harmonic, the degrees of freedom of the harmonic bath, that is nothing but the generating functional for the harmonic oscillators, which is ZSHO. And now one can evaluate this generating functional for the thermal bath in perturbation theory in the sources, and the coefficients that appear in this expansion are basically these contour correlators. And then one can employ this column vector representation to express these contour correlators in terms of the Whiteman correlators. But we should be careful about this fact that I mentioned, that the expansion that we have right now do not include these cases omega equal to 0. And once one has this column vector representation, one can evaluate these independent endpoint Whiteman, and if one can, for simple harmonic oscillators, it's very easy to calculate the independent endpoint Whiteman correlators, and that then one immediately has the influence functional. So yeah, so the future directions, there are some future directions that I mentioned. This column vector representation should be extended to the case omega equal to 0 to calculate influence functional when the coupling to the thermal bath is quadratic or higher power, and this one should extend this representation to general endpoint functions if one wants to calculate up to arbitrary order in the perturbation theory, and also address the questions that I posed at the beginning, where the motivation for studying this influence functional, and extend this analysis to more complicated thermal baths, which for instance are a bath of anharmonic oscillators. Yeah, thank you.
The correlators of your system on some contour.
Yeah.
Do you need to know the correlators of the bath only on that same contour?
Yeah.
Any more questions?
Sorry, one more follow-up question. Suppose we were just at 0 temperature.
Yeah.
And I wanted to compute some retarded correlator. Some insertion of a retarded correlator, some commutator with a theta function inside some bigger correlation function. That generally requires you to be on a strange contour even at 0 temperature.
Yeah.
Now, in order to see suppose I had two fields, like a light field and a heavy field.
Yeah.
And in order to see that thing vanishes outside the light cone, I would also then have to integrate out the heavy field on that strange contour. Is this right? If I just integrated out the heavy field in Euclidean space, just naively, and then use that effective action to compute this,
The commutator.
Commutator, will I get something non-vanishing outside the light cone if I did that wrong calculation?
I don't think so, but yeah.
Sorry, you do or do not think so?
I don't think so.
So if I just do the normal effective action calculation and then I use that to compute this you think it will still vanish outside the light cone? I thought the right thing to do would be to integrate out the heavy field on the same contour like you're saying here.
Oh, you're saying that you don't integrate out.
You do what you normally do. You integrate out the heavy field in
Yeah.
Time ordered way. Then you use that effective action to compute this funny correlation function. Presumably you'll get the wrong answer. Is this right? You'll get things non-vanishing outside light cone. Is this right?
I haven't. You're saying that from Euclidean theory one can't get this information. I mean that.
Normal effective action integrating causality. Perhaps to that intent.
So saying that one could actually do this Schwinger-Keldysh formalism, generalized Schwinger-Keldysh formalism.
That is correct. That is to use it to compute time-ordered correlators of the light.
Yeah. So if there are no further questions, let's thank Soumyadeep and go on to our next speaker, who's my